And it is a pleasure to have Peter Bouwknegt from ANU, and he will give us a pedagogical introduction into T-duality. So thanks for accepting our invitation.
Okay, thanks, Johanna. Well, first of all, thanks to the organizers for inviting me to give, I think, the second seminar in this series. Yeah, I'm really looking forward to a year of math physics seminars. I'm a bit depleted here, deprived from input, so I'm looking forward to other people talking as well. So I want to talk about T-duality today. I'm looking at the list of participants. So my idea was, so T-duality is something I've been working on for the past 15 years on and off, and it's still a topic that keeps on giving. So I'm still having various projects in the area. Unfortunately, none of them has reached the state where I can really talk about it. So what I proposed to do was to just give a pedagogical introduction. So this is really something that's aimed at people that have only vaguely heard about T-duality. Now, I see a lot of people in the participant list who know much more about T-duality than I'm going to cover in this talk. So at some point, if you feel like, okay, I can't stand it anymore, feel free to just leave the seminar and maybe watch the recording to quickly speed through the seminar on your own time. Yeah, so the T-duality. So let's see if my computer works. I realize it's Friday the 13th, so something is bound to go wrong. Anyway, it seems to be working still. So, so what I want to do today in today's talk, again, this is a talk that the experts might have heard some version of already. So again, I apologize. So there's a lot to say about T-duality. I really want to focus on more the developments that I've been involved in and my collaborators. And because T-duality basically originated in the 70s, I sort of got involved 15, 20 years ago. And the particular aspect we got involved in was what is now called topological T-duality. So these are really topological consequences or aspects of T-duality. So I haven't really said what T-duality is yet. So T-duality is a symmetry of string theory. It's become very important in identifying equivalences between different string theories, or string theories which we thought were different. So it's actually symmetry between the full theory. So it's more than just topology, I want to emphasize. The mathematical developments have been mostly centered around topological consequences. So there's a lot that one can say about topological T-duality or applications in mathematics. It shows up in lots of context, in differential geometry, in C-star algebras, noncommutative geometry, algebraic topology, etc., etc. My talk will be mostly focused around aspects in differential geometry, because that's probably the area that most people are familiar with. So I'll spend quite some time in introducing T-duality, both from a mathematical and a physics perspective, and give some examples. And then I will focus on two more recent developments. I mean, not very recent, but still last 5 to 8 years. So one is spherical T-duality, which is a generalization of the T-duality of the first half of my talk. And the other is an attempt to do T-duality in cases where there's no isometry. So this should be clear throughout my talk what I mean by this. Okay, so I want to introduce T-duality. Okay, I should mention some of my collaborators. So most of the papers I'll be talking about, most of the work has been done in collaboration with MathI in combination with various other people. I'm going to skip most of the references. If you're interested in getting some references to other work, then please contact me over email, and I'll just give you point you to the right papers. Okay, so I want to introduce T-duality as a generalization of Fourier transform. And please feel free to interrupt me if I'm going too fast or if you can't hear me or whatever. So Fourier transform, well, this is something everybody's familiar with. I'm not going to state precise conditions for the existence and convergence of integrals and series. It's more the idea. So Fourier series, first of all, yeah, this works. We can look at periodic functions or functions on the circle. In that case, we can decompose those functions in terms of Fourier modes, f hat n, where e in the power I n is the complete set of functions on the circle. And you can calculate the Fourier modes by what is called the Fourier transform. So that's the first equation here. You just take the function, you multiply it by a function e in the power I n x, where n is an integer, and you calculate that integral, and that gives you the particular Fourier transform. So Fourier transform in this case is a map, if you want, from functions with satisfy certain properties, but functions on a circle to functions on the integers. Of course, this can be generalized quite substantially, but no. Sorry, something is going wrong with my. Oh. I should be able to swipe, but it conflicts with my pen. So let's see how we do that. Okay. Just bear with me. I knew something like this would happen. Okay, there we go. Sorry for that. So we can generalize this to, say, functions from the real numbers to the real numbers. In that case, the Fourier transform is another function on the real numbers, and you're probably all familiar with the corresponding formulas. Okay, so more generally, we can define Fourier transform. Having the same problem again. Sorry. This probably takes, yeah, let's should do it with 2 fingers. No. Does anybody know how to do this? I should stop the pen to work some way. Okay.
There looks to be a button at the top right, which allows you to switch pages.
Do you think that's it? Oh, okay, that works. I was using the button on the lower hand, but that doesn't work. Oh, okay, thanks. Good. Okay, where was I? So we can generalize this to functions on any locally compact group G, abelian group. In that case, the Fourier transform becomes a map from functions on G to what I call functions on the Pontryagin dual. And the Pontryagin dual is the following thing. It's also called a character group of G. So it corresponds to the group homomorphisms from G to U1. So those are characters. Those are functions satisfying this homomorphism property of the group G, which I've written as an addition here, and the group U1, which I've written as a multiplication. So the formulas look all the same as we used to have. So that's easy. Now, I think that's a bit fuzzy, but okay. Does everybody see this fuzzy? How can we do that? That I've seen before.
Yeah, a bit. But it's readable.
Okay. Strange. Ah, that's better. Okay, so the Pontryagin dual is in itself also a locally compact abelian group, just under the pointwise multiplication of characters. So in my previous examples, the first example, I had the group G to be S1, and then the Pontryagin dual is the group of integers. And my second example, the group G was R, and the Pontryagin dual is in that case also R. And the characters in the first case are given by e in the power I and x. That's a complete set of characters for an integer. And in the second case, a complete set of characters for the group G are the functions e in the power I bx, where p is a real number. So in some sense, this function e in the power I px, or e in the power I and x, can be sort of considered as a universal object which encodes all the different characters of the group G when p runs over the group G hat. Okay, so and Fourier transform, as we all know, expresses the fact that the characters of G span the functions on G. So you can expand any function on G in terms of its characters. But let me see if I can easily go back. Yeah, if you look at this formula over here, there's something strange happening. Because somehow we can think of Fourier transform as a black box if you want. You start with a function on G, and then you put it in this black box, and what comes out is a function on G hat. But if you look closely at this black box over here, what you're doing is you start with a function on G, then somehow you multiply by a function both on G and G hat, and then you integrate away the G dependence. So there's sort of an intermediate step happening here, where I interpret the integrand not just as a function on the original G, but as a function on G cross G hat. So formalizing that mathematically, this is what is called a correspondence. So now I have a very compact way of writing Fourier transform. I start with a function here, I pull it back to a function on the correspondence space. So that's what's happening here. Then I multiply it by some function e in the power I px in my case, some kind of universal object, and then I push it forward, in this case by integration over the group G, to get a function on G hat. So the reason I'm formulating it this way is because we'll see that T-duality has exactly the same form. So T-duality really is a generalization of Fourier transform. And if you want, it's a generalization or some geometric version of Fourier transform, where you replace functions by geometric objects. For instance, bundles or something more complicated, D-modules, coherent sheaves, or something like that, or maybe objects or the characteristics of such objects like cohomology, K-theory, derived categories. So in order to illustrate that, I'm going to do a very simple example, and we'll see that this example is actually closely related just to ordinary Fourier transform. It's so simple it's almost insulting, but what I'm going to do is I'm going to look at particular transformation on cohomology of a space which is the product of two manifolds, a manifold M and a manifold S1. S1 is really what the manifold which occurs all over the place in T-duality. So we're going to do T-duality in this particular example with respect to this circle over here. Okay, so by the Kuhne theorem, the cohomology of the space P is just the product of the cohomology of M and the cohomology ring of S1. The cohomology ring of S1 is concentrated in degree 0 and 1. So if we look at the cohomology of P in degree n, it just consists out of two copies. One copy of a cohomology of M in degree n and another copy in the degree n minus 1. Or to make this a little more concrete, this also holds at the level of invariant forms. We can decompose invariant forms on P in terms of degree n invariant, in terms of degree n forms on M and degree n minus 1 forms on M. So concretely, the generator of the cohomology of S1 is just d theta. So this decomposition over here is just thinking of forms on invariant forms on P, either as forms on M or forms of the type where omega is an n-1 form, wedge d theta. So in other words, invariant forms on P come in two varieties. They come in terms of forms on M or forms on M wedge, the generator of the first cohomology of S1. And now we can do a very stupid thing. We can just, maybe before I do that, we can just interchange these two pieces. And that's what I will call T-duality. So interchanging these two pieces, the n and n-1 piece, is of course not degree preserving, but it transforms even forms into odd forms and odd forms into even forms. And what I'm going to argue is that we actually have an isomorphism, which I call F for the analog of Fourier transform, between the forms on P of degree I mod 2 and degree I plus 1 mod 2. So between the even and odd forms and the odd and even forms, where P hat is, in this case, the T dual, which is in this case just M times another circle, which I'll call the dual circle. Okay, so concretely, so H0 is just the even forms, H1 are just the odd forms. My map is just, well, as I said, I take an n form here and I map it to an n+1 form, so a form of the other type with the dual circle. And for the n-1 forms, wedge d theta, I map them to an n-1 form omega. So this is an obvious map, which is the inverse of itself. So this is a duality. And I claim this duality preserves, acts as an isomorphism on these cohomologies, which you can easily verify in this case. Okay, so what does this have to do with Fourier transform? So let me just rewrite these equations as one equation. And it turns out that's not that hard. We can write it as follows. So omega is either this omega or this omega. So is a general element of the cohomology or a general invariant form on P, on M cross S1. If I multiply by this particular factor, you can see that in cases of this type, first type, I will need to, in order to integrate it over d theta, I will need to pick out this particular term, and then the answer will be something like d theta hat wedge omega. And similarly for the other term, in that case, to get a non-zero answer, I have to pick out the 1 here, and then I integrate away the d theta, and I get omega. Now, if I massage this equation a little bit, I mean, 1 plus d theta wedge d theta hat is just the exponent. The exponent in this case, if you expand it, it just has two terms, just because d theta wedge d theta is 0. Or in other words, it's of the type e in the power sum 2 form times omega. And this exactly looks like Fourier transform. It's also the exponent of some kind of, well, in this case, it's a 2 form, but exponent of something that lives on a space containing both the circle and the dual circle, which you multiply by omega pulled back to that space. So in other words, what's happening here is that this particular transformation is given by, well, you pull back, maybe I'll bring up the diagram here. You pull back a form over here to M cross S1 cross the dual circle. You multiply it by this e in the power f, which was e in the power d theta, which d theta hat. Then you push forward by integrating away the d theta, and you end up with a form here. So the form of this transformation looks exactly the same. In this case, it's not for functions; it's for forms, if you want. Now, in what sense is this formula sort of universal? Well, you need to know a little bit about differential geometry, but it turns out that this particular 2 form has a geometric meaning. It's the 2 form of a particular bundle, the Poincare line bundle, which is the generator of line bundles over the circle across its dual. And in fact, e in the power f is nothing but the Turing character of this line bundle. So this particular formula, which I write down here, actually has a very nice geometric meaning. I take a form, pull it back to the correspondence space, and then just multiply by the Turing character of a particular fixed line bundle over S1 cross S1 hat. Okay. Now, once you realize that, that the geometric objects in this case are just line bundles, you can also try to generalize this particular T-duality or generalization of Fourier transform to the actual objects. So what you could try is take a vector bundle, pull it back to a vector bundle over the correspondence space, multiply by this line bundle, and then push it forward to get a transformed vector bundle. Except that's a bit simplistic. This push forward is in general not defined on vector bundles. So what you have to do is go to K-theory. So if you don't know about K-theory, think of it as equivalence classes of pairs of vector bundles. So the thing that is well defined is the map on K-theory. So by generalizing my simple cohomology example to objects, I get what is called a T-duality between the K-theories of P and P hat, where P hat was just topologically the same space, but with a dual circle. But what the Fourier transform does is it changes the degree of the K-theory, so it maps odd to even and even to odd. Okay. Okay, so this is actually called Fourier-Mukai transform in the literature, in the math literature, and this can be generalized to other cases such as derived categories or whatever objects you fancy. Okay, so I want to take a step back and both generalize this and to show you where it comes from. So it comes from physics, from string theory. So let me tell you a little bit about string theory. You don't have to have any knowledge about string theory, but just pictorially you'll probably understand what it means. So, so this comes from closed strings moving on a space-time which contains a circle. So a closed string is something which looks like this, say, and if it moves, it spans out some kind of two-dimensional, well, you can split and join, some kind of two-dimensional surface. And in a sense, a string theory contains how this two-dimensional surface called the world sheet is embedded in space-time. So string theory can have other degrees of freedom. The space-time can come with particular structures like a complex structure or whatever, and also the world sheet can come with different kind of structures. But string theory always contains this embedding of my world sheet of a string in terms of into space-time. So if a space-time contains a circle, then, well, in general, you can't really quantize a string exactly for arbitrary space-times, but you can do it in the circle direction. And what happens in the circle direction? Well, one thing that happens is something you're familiar with, hopefully, that if you have a compact space, then the momentum corresponding to that direction is going to be quantized. That's just what is called Bohr's quantization rule. That's how you can calculate the spectrum of the hydrogen atom, for instance. And the momentum modes are going to be quantized in units of 1 over r. So in this analysis, I'm forgetting factors of 2 pi, so there might be some factors of 2 pi hanging around. But essentially, it's momentum has to fit an integral times into the circumference of the circle, so it needs to be quantized in units of 1 over r. So that's what happens for point particle theories as well. But for strings, something interesting can happen. So if you have a space-time, now I want to draw a space-time which is higher dimensional, but I can't, so it really looks like my two-dimensional world sheet again. But if you have a string, it can wrap around this circle in space-time. So that's another global mode of the string, which is also dependent on r. So in terms of boundary conditions, you could say that if you go around the closed string from, say, sigma, this coordinate sigma, which goes around the closed string like this, from 0 to 1, then it can wrap m times around the circle in space-time. So that's this m, which is called the winding number. So if you look at the spectrum of a string, you see this circle of radius r here, occurring in two ways in the spectrum. You see it in the quantization of the momentum mode in the direction of that circle, and you see it in the fact that there's states in the spectrum which are stable, which correspond to winding m times around the circle. But of course, there's many other states in the spectrum corresponding to oscillations of the string and what it does in the other directions. But if you write down the spectrum, the R dependence is sitting in two places. There's this place coming from the momentum mode, so that's essentially the kinetic term, so that's like p squared over 2 if you want. And then there's the part of the spectrum, of the energy spectrum, that comes from these winding modes. And that, of course, goes like mr squared. It has to grow with r because the bigger the radius of the circle, the more energy it costs to wind around that direction. Okay, now curiously, you see that the spectrum is invariant if I perform a duality r to 1 over r. And in fact, that's not just true for the spectrum. You can actually show that it's true for the whole string theory, for all scattering amplitudes, etc. So this is really a symmetry of the string theory. R goes to 1 over r. And this is T-duality in its simplest form. Now, this is just for bosonic strings. In general, T-duality can act between different string theories, in particular when you have superstrings. So, for instance, if you know a bit about superstrings, there's a type 2a and 2b. This T-duality actually becomes a symmetry or duality between type 2 and type 2a and type 2b. Okay. Okay, so before I show the next slide, I have to say a little bit more. Okay, so that's just for circles, and I mean this part of the duality was known, has been known for probably 40 years, so there's nothing new there. But what turned out to be interesting, which we developed with Metha and collaborators, as I said, some 15, 20 years ago, is when you don't take space-times which are globally products of manifolds with a circle, but where you have sort of locally defined circles. So in mathematical language is when you're considering circle bundles. So this analysis of what happens in the circle direction is really a local analysis. So you could consider situations where the circle is sort of twisted over the space, so where you have a non-trivial circle bundle. And the other generalization which we did was not just look at strings in a say a vacuum background, but look at strings which move into, say, a background flux, which is the analog, the string analog of electromagnetic flux. So strings don't couple to just one form connections. Strings couple to two form connections because they need an extra dimension to couple to. So the analog of an electromagnetic flux in string theory is the curvature corresponding to a two-form connection, so it's a three-form. So the setup that we considered was the following. So instead of a trivial circle bundle, we take, in general, a non-trivial circle bundle, P, and we take a three-form H defined on this circle bundle P. So P plays a role of space-time here. So P, if P is trivial, it's M cross S1, otherwise it's non-trivially fibered. So there's two ingredients. There's, well, from a topological perspective, the ingredients are, say, an isomorphism class of principal circle bundles over M, and H is a cohomology class, a flux on P. So you can take it quantized, or you can take it to be a check cohomology class, or if you don't know what check cohomology is, think of it as a de Rham class, or just think of it as a closed three form. So it turns out, and I'll come to the physics derivation of that later, but it turns out that if you do T-duality in such a case, that the dual is not is not the same circle bundle. The dual turns out in this particular case to be another principal circle bundle, say p hat, or in general another principal circle bundle p hat, with another background flux. And there exists a very explicit simple formula for the dual. So recall H was some kind of 3 class on P. I can push it forward in this particular, in the original diagram, I can push it forward. So in terms of cohomology, it's just, if you want, just integrating over the circle. So that gives me a form or a check class of 1 degree lower. So that gives me a 2 class on M. So this 2 class defines for me an isomorphism or an isomorphism class of another circle bundle, which I've called P hat. So this topological transformation doesn't actually give me a concrete dual circle bundle. It gives me an isomorphism class of circle bundles defined through its its first Chern class. And the dual flux is satisfying a similar relation is such that if you do the same push forward in the dual diagram, you get the original first Chern class back. Now that of course doesn't completely determine H hat. There's another little ingredient you need over here, and that ingredient goes again through a correspondence. So this brings me back to why this more general case is in fact also a generalization of Fourier transform. So the ambiguity of H hat, well, if you think about what T-duality should do, T-duality should only do something with the components of the original flux, which are in the direction of the fiber, and not the component of H, which just lives on M. So in some sense, I want to say that H hat should have the same component on M, but have a transformation in the directions of the fiber. But H and H hats live on different spaces. H lives on is a 3 class on P. H hat is a 3 class on P hat. So you cannot just directly compare them. I sort of want to say that I want to compare them on M, but to do that, to decompose them in things on M, which we'll do later, you have to look at invariant 3 classes, which I haven't assumed yet. But there's another way of comparing them. That's by pulling them back to the correspondence space. So in this case, the correspondence space is just the fibered product of P and P hat. So by the fibered product, I mean the Cartesian product, such that X and X hat map to the same element in the base space M. So you can pull back both H and H hat to this correspondence space, and the extra requirement, which turns out to be equivalent to the fact that the components on the original base space should be the same, is just the requirement that on the correspondence space they should be cohomologous. So the difference should be 0 in cohomology, in the 3 cohomology of this correspondence space. Okay, a lot of words. I hope you're still with me. So again, I will give a physics derivation of these statements later. But for now, I want to see how they fit into something that maybe people in algebraic topology might know. So that's the so-called Giesen sequence. And again, sorry if I'm annoying people because they've heard this talk before. Feel free to leave and just catch up on the recorded version. So circle bundles come equipped with a long exact sequence, which is called the Giesen sequence. And I've written down part of the long exact sequence in this first row here. So the cohomology here can be either the round cohomology or check cohomology. That doesn't matter that much. It could be with Z coefficients or with Z2 coefficients. In any case, so whatever you feel comfortable with. So what I've been doing fits nicely into this Giesen sequence because my background flux H was sitting in the 3 cohomology of P, and I told you that if I push it forward, I get something which I identify as the dual Chern character, the dual first Chern class of the dual bundle, which is an element in the 2nd cohomology of the base space. So this particular push forward satisfies a nice property that if you follow it through with the next map in the Giesen sequence, which is called the connecting map, it goes to 0. So once you have that, you can write down the Giesen sequence for the dual bundle, which looks the same way, except that now the maps are all given in terms of data of the dual bundle. So we had F hat sitting here, which came from H. So in the dual bundle, in this Giesen sequence, we can look at the original F over here. We know this maps to 0 because that follows from what it does in the first Giesen sequence. So we know, because of the exactness of the sequence, that it comes from an H hat over here. And that's precisely my duality. And again, this H hat is not uniquely determined. It's determined up to an element that comes from here. So it's determined up to an element in H3M, and I've just tried to fix that element in H3M by imposing another condition. And if you want to play around with some algebraic topology, with some diagram chasing, then I urge you to see that the condition I imposed, so the fact that H and H hat should be identical in the correspondence space, essentially uniquely fixes H hat. And you can do that by, I'm not going to explain this diagram, but the standard trick is to go to a double complex. So this double complex has both the original Giesen sequence and the Giesen sequence for a dual bundle, and then it has a Giesen sequence for the corresponding circle bundles defined through the correspondence space. And you can, by a bit of diagram chasing, so H hat was sitting here, H is sitting here, compare them over here and say over here they should be the same. You can chase it back and conclude that uniquely determines them. Okay, so I'm not going to go through that. I just want to give you an example and emphasize why this is well, a generalization of what I've been doing before, but also why it's a very interesting generalization. So the simplest example where you have both non-trivial circle bundles as well as 3 fluxes on the bundle space is the case of a 2-sphere, or maybe a 2-torus is also very interesting. Let's do the 2-sphere. So the 2-sphere has cohomology, 2nd cohomology, which is the integers. So isomorphism classes of circle bundles over S2 are classified by an integer, and the bundle space is a 3-dimensional compact-oriented space, so it has a 3 cohomology, which is also the integers. So there's 2 sets of integers at play here. So let's look at the first example. So first, the trivial circle bundle. So this corresponds so the trivial circle bundle, but also with trivial flux. So let me call this integer m, this integer n, then this corresponds to mn equals 0, 0. Okay, so this corresponds to the case that was my prime example of how T-duality in the case of trivial circle bundles is just a generalization of Fourier transform. Now, if you go through my formulas, it's not hard to see that what my duality is just interchanging the role of m and n. So in this case, since m and n are both 0, the dual is the same space, and that's what we used to call S1 hat. So this is exactly the same example as I had before. But here's a slightly more interesting case. This is the case where I look at the trivial circle bundle, but now I take 1 unit of flux, so 1 unit of electromagnetic flux in which the string moves. Then the duality moves it to 1 unit of Chern class, which in this case corresponds to the Hopf bundle. So this non-trivial non-trivial bundle, which is corresponds to over S2, which has during class 1, is this Hopf bundle that hopefully people are familiar with. But now with zero flux. So the T-duality here changes the topology of the space. S2 cross S1 clearly has a different topology than S3. Yet what I'm claiming here is that if you look at strings moving in these two configurations, so if I look at a string moving in S2 cross S1, in the background of some amount of flux, I don't see the difference between a string moving in S3 with zero amounts of flux. So string theory, and again, that's not just true for the spectrum, it's true for the whole string theory. So string theory in some sense can't distinguish between topologies so between topologies of certain manifolds. Really the string theory moving in these two spaces of different topologies but with different amount of background flux are indistinguishable from a string theory point of view. So in some sense, saying that string theory moves in a certain space-time is the wrong concept. We really should try to reformulate string theory if you want to sort of use the full power of this duality in terms of, say, degrees of freedom, which are obviously T-duality invariant. We shouldn't choose a fixed background and then quantize the string in that background, because that obviously the string doesn't really see the complete background, it just sees sets of degrees of freedom. Okay, so this is a particular example of more general example of I shouldn't have called these, so now I'm calling these P and K, of a circle bundle over the two spheres, so-called length space of order P. If you take the length space of order P with K units of 3 flux, then the dual will be length space of order K with P units of 3 flux. So length spaces for different P and Ks are topologically not the same. Okay, so again, this is something quite surprising. T-duality can change the topology of space-time. And string theory doesn't see the difference between those two string theories moving in those two manifolds of different topology, provided the fluxes are such that they compensate for the difference. Okay, but as I said, T-duality is more than just topology. So it actually acts on the forms themselves, and then we will see how it looks like Fourier transform. So we can choose particular representatives for these cohomologies, and particularly we can choose a representative which is an invariant form. And as I said, invariant forms for trivial circle bundles can be decomposed in terms of forms on the base and forms with 1 degree lower on the base. But even in the case of non-trivial circle bundles, you can do that as long as you do that not with respect to d theta, but with respect to a connection on the circle bundle. So this is something which physicists would call dimensional reduction. So you can do this for non-trivial circle bundles as well, as long as you take a connection on your principal circle bundle. So how does T-duality look with these specific representatives? Well, it's very simple. So if you decompose the 3 form in terms of a 3 form on the base plus a 2 form on the base using this connection, and T-duality, the dual F, is just this particular part of H. So you only take out the part that has a component, has a lag in the fiber direction. You don't do anything with this H3. The dual flux is just the same H3, but now you see that what used to be H2 here is now interchanged with this this over here. So that in terms of explicit representatives, it's quite clear what you're doing. And if you, for instance, now take the difference of H and H hat, you will see that that's a co-boundary in the round cohomology. So it is actually, the difference is trivial on the cohomology on the correspondence space. Okay, so this looks all a bit like abracadabra. I've already alluded to the fact that the string theories on these spaces with these backgrounds are equivalent. But here's some mathematical consequence, which you can prove independent of string theory techniques or knowledge. So the simplest consequence of that is that there's an isomorphism now between, well, we had an isomorphism in the trivial circle bundle case between cohomologies Z2 graded cohomologies, even odd forms. It turns out that with this background flux, the cohomologies are cohomologies with respect to so-called twisted differential operators. So this twisted differential operator also satisfies dh squared equals 0 because of the fact that dh equals 0 and h wedge h equals 0. Because h is an odd form. Of course, dh doesn't act on forms, doesn't preserve z grading because d increases the grading by 1, while a cupping with or wedging with h increases the degree by 3. So it maps even to odd and odd to even forms. Okay, and how does this transformation work? How does this isomorphism work? Well, here's an explicit formula. If I take an invariant form and I do this particular transformation, so I pull it back to the correspondence space, which I've not explicitly done in this formula. I multiply it by this universal object, which is now the generalization of d theta wedge d theta hat. But I need a connection on the circle bundle. Then you can show that this particular T-duality or generalized Fourier transform intertwines with the twisted differential operator, and that's essentially because the derivative of a wedge h hat intertwines between the h hat and h. Okay, so this is a very simple theorem. In particular, it shows that that the twisted cohomologies of P twisted by H and of the dual P hat, which has a different topology in general with the dual flux, that these two cohomologies are isomorphic with a degree shift of 1. So this is a mathematical consequence, and you can just the proof is essentially given here. It doesn't rely on any intuition about T-duality. Yet it does equate cohomologies on totally different spaces. And in fact, this particular twisted cohomology might not be that interesting, but if you, for instance, look at an object called twisted K-theory, it turns out you have a similar isomorphism. A twisted K-theory sees torsion and is therefore more interesting. And in fact, such an isomorphism can be very useful to actually compute, say, the cohomology of P if it turns out that the twisted K-theory of P hat is much easier to compute. So that has, for instance, been used in the example of the computation of K-theories for groups by Paralia Hekmati, if I'm not mistaken. So for instance, in the case of the lens space, where we already knew what T-duality was doing, it turns out the twisted K-theory of the lens space, twisted by K units of flux, is Zk in degree 0 and Zp in degree 1. So indeed, the dual, I said, interchange K and P, so that is precisely this isomorphism over here. I'm looking at the time. Okay, it's going very fast. So here's basically where my review of K-theory ends. There's something happening with my iPad. Gee. Yep. Sorry. So now I want to talk a little bit about more recent results. So one thing you might wonder is why is this so relevant to string theory, this particular circle bundle and T-duality, etc. So that's what the first column is supposed to convey. So in string theory, we typically work with, or superstring theory, we work with 10-dimensional space-times. And in order to make contact with the real world, we often look at string theories defined on 4-dimensional Minkowski space times some 6-dimensional compact space. Or generally, you don't have to take it compact, but in general, it's taken compact. So that its size is small and you don't really see the consequences in our real world, only at very high energies. Now, depending on the structure on the 6-dimensional space, you preserve certain amounts of supersymmetry in the theory, which you might either like or not like. So for instance, in order to have n equals 1, n equals 2, or n equals 3 supersymmetry, you need to look at various kinds of structures, such as scalar manifolds, Calabi-Yau, hyperkähler. In case there's background fluxes, these things really are not strictly Kähler, but they're called generalized Kähler and similar terminology. Now, for some reason, it turns out that all these examples that physicists are interested in often have S1s in them. So Calabi-Yaus are often toric vibrations, etc. So there is S1s naturally floating around in these physical theories, and as we've seen, S1s they like strings because strings can wrap around them, and strings are coupled to a 3 flux. So these are all sort of things which seem to nicely fit into a picture. So you can do T-duality around these S1s, or if these S1s degenerate, you have to go to algebraic geometry and you look at more general things, which are called mirror symmetry, but it's essentially just souped-up versions of T-duality. And there's a particular geometry associated with all of these constructions, which nicely encodes this T-duality, which is called generalized geometry. In some generalized geometry, treats momentum modes and winding modes at an equivalent level, so you can easily, so they're very natural generalizations of geometry that sort of encode the T-duality aspect. And as I said, the simplest example of manifolds you might be interested in, well, these are not 6-dimensional manifolds, but there might be a subset, a submanifold of 1/6. So you might ask, everything I've done so far, is it very specific? I mean, does it only work for circles, or maybe circles of higher rank, tori, or could there be other ways of T-duality in physical theories? And a natural thing to look at would be M-theory. So M-theory, or its low energy limit, 11-dimensional supergravity, you typically would consider it on 4 manifolds times 7 manifolds. So these can't be complex manifolds, these 7 manifolds, because they're all dimensional. But it turns out that if you want to preserve some symmetry, there's a similar list of particular structures that play a role in odd dimensions. And in general, they go under the name of contact manifolds. So the analogues of Kähler, you need to take them Sazakian or Sazaki-Einstein or 3-Sazakian. And it turns out, well, actually these compactifications were studied before string theory. People were studying 11-dimensional supergravity. So in some sense, the story on the right-hand side is much older. And for some unknown reason, it might be just because the examples are easy to construct, but these contact manifolds often has 3 spheres in them. So it seems like the picture for M-theory is maybe quite similar to for string theory, except for 3 spheres. And there's more numerology here. So 3 spheres, so while S1s are naturally wrapped by strings, by 1-dimensional objects, 3 spheres are naturally wrapped by 2 branes. 2 branes have 2 spatial and 1 time dimensions. So M-theory and 11-dimensional supergravity have 2 and 5 branes. So the 5 branes also play a sort of role. If you would take a 5 brane and wrap it around S3, and you would look at it from a very far distance, so where the 3 sphere is very small, then what you would see is just 2 of the directions of the 5 brane. So you would actually see a 2 brane from far. So it looks like there might be some kind of duality between 2 and 5 branes in the presence of 3 spheres. The other nice thing is 5 branes coupled to 7 fluxes, in the same way as strings coupled to 3 fluxes. And it turns out there's a natural Giesen sequence again, which deals with S3 principal bundles and 7 fluxes. So So it seems from a lot of numerology that there might be something happening in M theory. And in fact, from the mathematics perspective, you can do this topological T-duality, and I'm starting to run out of time, so I'm not going to go through all of this in detail, but it turns out there exists Gießen sequence for sphere bundles in general, but in particular the one for principal SU2 or principal S3 bundles is interesting. So the part of the Gießen sequence that's relevant is taking 7 fluxes, pushing forward over the 3 sphere, getting a 4 class, which is almost the same as saying that you have a principal S3 bundle or an isomorphism class of principal S3 bundles, but not quite. In fact, there's no, and the correspondence between principal S3 bundles and 4 classes, so it's the second Turing class, is neither injective nor surjective, but it depends a bit on the dimensions which you're working in. And there is a close correspondence between this 4 class and any principal SU2 bundle, of course, has a 4 class, the so-called second Turing class. But again, this correspondence is not one-to-one. But you can set up things like twisted K theory, twisted cohomology, and a lot of the mathematics just go through. Unfortunately, despite my best effort and other people's best efforts, we haven't really found this as a symmetry of M theory yet. It seems to be either just a mathematical curiosity, which somehow has the numerology of M theory, but it doesn't seem to be a symmetry of M3 itself. At least so far, we haven't found a clear indication of that. Okay, so what I had planned to do, it's now 5 o'clock, is to actually give you a derivation of this T-duality from a physics perspective. So to derive these T-duality transformation rules, but yeah, to go through that probably takes me another 15 minutes. So I think I'll hand over to the moderator and see what she thinks of that.
So I'm perfectly fine. It also depends on the audience. So of course the audience is free to leave, but I would be curious to hear more details.
Okay, then I'll just continue. And okay, if people need to leave or want to leave, had enough of it, just terminate the session. But so what I want to do is show you how to derive these T-duality rules. So again, T-duality is more than just topology. And what I'm going to derive is actual transformation rules on the fields as they arise in string theory. So in order to do that, so I can't, in general, exactly solve a string theory as I did for the string theory on a circle. But what we can do is sort of write an effective model. It's called a nonlinear sigma model. So the embedding of my string world sheet into space-time. So yeah, so I use the name M and P interchangeably, but it's P in my previous notation, where P can be, say, for instance, a circle bundle over M. Well, these sigma models are defined by, well, in general, they will involve a metric on P, so a Riemannian metric. If you had just the part with the Riemannian metric, then the equations of motion would just be harmonic forms on this space P, but in general, P comes equipped with additional information, such maybe as complex structures, scalar structures, etc. But a particular piece of information which we've been using is this coupling to this generalization of electromagnetic fields, so coupling to a 2-form. So I'm looking at sigma models of this particular type, where the additional information on P is a Riemannian metric and a particular locally defined 2-form with a globally defined 3-form flux. Okay, so what I want to do is say have some maybe some vector fields acting on P and see when they give rise to symmetries of this action. So physicists like symmetries. If they have symmetries, they well, they have the better control of the model. but also they might correspond to something physical. So let's assume that we have a set of vector fields. So on P, so written in terms of local coordinates as follows, which satisfy a particular Lie algebra under the Lie bracket of vector fields. And let's consider infinitesimal transformations of my coordinates in the direction of these vector fields. So sorry for the index notations, physicists will know what I mean, but mathematicians might want to just omit the indices. So VA here, I'm using the index A just as a set of vector fields, but you could say those are the components of a vector field in a basis of the Lie algebra G. So if you look at the variation of the action that I've given before, under this particular transformation, you'll see that, well, the variation of the coordinate shows up both in the variation of these differentials, but also shows up in the variation of G, because G depends on the coordinates, and miraculously the variations combine into Lie derivatives. So there's a very simple case in which such a model is invariant under such transformations generated by vector fields. Namely, if the Lie derivative of these vector fields of the metric G is 0, so when these VAs form a set of killing vector fields, and when the B field is invariant under these killing vector fields. Okay, so now that we have identified potentially a set of symmetries of this sigma model, in particular, let's say for when there are circles where we have just U1 killing vector fields acting on my manifold, we can do something that physicists like to do. Once they see symmetries, they like to gauge them. So this is the idea behind gauge field theory, where you make certain symmetries local. That's what's so the symmetry I have here is in terms of a set of constant epsilon, but epsilons, if you try to make them local, so if you try to make them dependent on sigma, so if you try to make them functions of sigma to the Lie algebra, then of course there's additional terms that are occurring in a variation of the action, and it turns out you can compensate for that by introducing more degrees of freedom, by introducing a so-called connection, and make your derivatives covariant derivatives. And in general, this process you might need to add a lot of extra correcting terms, but this particular symmetry is simple enough that it turns out if you replace your derivatives by what is called covariant derivatives, then the action, which looks like the previous action, but all derivatives just replaced by covariant derivatives, is actually invariant under local transformations. So transformations where the epsilons are can be dependent on sigma. And for that, you have to choose particular transformations of these connections. And the formulas, well, again, I've written them both in a sort of invariant notation and with respect to a basis. These are probably formulas you've all seen. This is just a covariant derivative of epsilon. Okay. Okay, so I probably need another 10 minutes. So so what we've done now to our model, put it here. So we now have a model where we've replaced the derivatives by covariant derivatives, introducing more degrees of freedom, an infinite number of extra degrees of freedom, namely these connections A, but we've also introduced an infinite number of extra symmetries because we've made our symmetries local. So in principle, it's a different model. It's in fact, you might say it's much more difficult because I have introduced an extra infinite set of degrees of freedom. And I've made my symmetries more complicated as well. But actually, this turns out to be useful. So this can be considered as a model in itself, as a gauged nonlinear sigma model. But there's also a way of souping this up a bit and make this model equivalent to the original model. And the way to do that is obviously if I this particular model is equivalent to the original model if I would just be able to put a to 0, because then the covariant derivatives return to the original derivatives. So I can maybe add a Lagrange multiplier which sets a to 0. Okay, that turns out to be not very nice because a is not gauge invariant. So so then my term with the Lagrange multiplier is not gauge invariant, which is not very nice. I lose the symmetries. But there's a way to do this covariantly, not by introducing a term that depends on that's just linear in a, but a term which puts the curvature to 0. So if we introduce this curvature of a, then it transforms covariantly. That just follows from the transformation rule of a, and we can compensate that by introducing an extra set of fields, often called auxiliary fields or Lagrange multipliers, which transform oppositely. So in mathematical language, they transform in the co-adjoint orbit, while the f's transform through the adjoint representation. And then obviously this term which I've added is invariant under my gauge transformations, and its equation of motion would put f to 0. Now f to 0 is not quite the same as a to 0, but it includes the solution a equals 0 plus all its gauge transformations, of course. But here you're basically stuck if you want to then solve for f equals 0. Just having infinitesimal transformations is not enough. You need to have global transformations. So you need to be able to lift the symmetry from a Lie algebra to a group G, and then the set of solutions of this particular equation is going to be, it's going to be in orbit under the gauge action. I should say I'm just looking at things locally. I mean, if you look at space-times with non-trivial topology, can you of course also have flat connections which are not gauge equivalent to the 0 connection. But for the moment, I'm just looking at things locally. Okay, so to give you a very concrete example, and that's the last thing I'll do. I can look at a particular example where I know of a G symmetry. I can just namely take our space-time to be a Lie group. In that case, I know that the Lie group has well, there's a left action of the Lie group and a right action of the Lie group. So there's in fact two group actions that I can use to do my gauging. And the corresponding nonlinear sigma model without the B field just looks like, I've written it in some kind of invariant language here. The metric I'm using is what I call bracket G, and I've written in terms of the Maurer-Cartan forms. So I can choose a basis of my Lie algebra and expand it in the basis, and the coordinates with respect to the basis will be my original XA's, but essentially I've written down the same thing, except that I've omitted the B field for the moment. So this has a symmetry. As I said, you can act on the group G by itself, to the left and the right. If I act on the left, you can easily see that this action is invariant. If I act from the right, it's in general more complicated. You pick up these adjoint actions, but in fact, if my metric is invariant under the adjoint action, or in other words, if it's a killing metric or killing form, then my action is also invariant under the right action. So let's do our process. We have say the right action, and we want to make this action local, so we want to gauge it. So again, this is the same formula as I've written down before. I've added an x hat f term, and now my symmetries are global. So these are my covariant derivatives. My symmetries are now global symmetries and not infinitesimal anymore. So the right action of G on itself, I need to take my connection to be transforming as follows, and as I said, my auxiliary field or my Lagrange multiplier needs to transform in the co-adjoint with the co-adjoint action. So now we can actually solve for the equation of motion of my auxiliary fields. So we can solve for f equals 0. And again, I'm not just looking locally, so the space-time has trivial topology, then the most general form of the solution will be of the following type. So it will just be a gauge orbit, a group orbit of the a equals 0 solution, or if you want, this is called pure gauge. And if you substitute that solution into my action, just do a little manipulation, you find that the action with that particular solution put into it is just a gauge transformation of the original action. We knew the original action was invariant in such transformation. So indeed, we get, if you want, an infinite number of the original actions back. So if you divide out by the volume of the gauge group, you recover the ungauged model. So what physicists say that is by doing this, is by adding this this particular term, which forces f to be 0, this model is going to be equivalent to the original ungauged model. But the nice thing about doing this is actually that there's different ways of manipulating this model. So the fact that we have more degrees of freedom and more symmetries allows us to sort of rotate this model in a bigger space, but still produce the other things which are completely equivalent. And one way of doing that is not first solving for A and then gauge fixing, but first solving for the equation of motion of A and then gauge fixing. So we do it sort of in an opposite direction. It turns out that the model you obtain is actually of the same form as we started with, but with a different metric. So this model, at least at the semi-classical level where we've done the computations, but it can be argued that this extends to some extent to the quantum level, leads to a sigma model with a different metric, but which is otherwise completely equivalent. So this is, I've done it for vector fields which in general form a non-abelian algebra, so I get this structure constant here. But if you do it for U1, you don't have the structure constant. So essentially what this is saying is that R goes to 1 over R. So this is a particular generalization of my 1 goes to 1 over R analysis. And I'm almost finished. I just want to show you how we get our previous results. So I've done a lot of this without a B field. You can add the B field, and in particular, if your isometry is just abelian, so either a circle or multiple circles at tori's, you can do this procedure as I've done for the Wessel-Witten for the non-linear sigma model based on a group G, and you find these following transformation rules. And let me just write and show it to you for a circle. So a circle, I've decomposed my metric and my B field in terms of directions in the circle. This is one in the circle, this mu is in the other directions, and these are the content of my formulas. So these are what people call Boucher rules. So they encode the symmetry of the sigma model coupled to a metric and a B field. And that's by going through the gauging of that sigma model. And then on the one hand, that model is equivalent to the original model by doing the gauge fixing in a particular way. But if you do it in a different way, you get the same sigma model for dual fields, which are given here explicitly on the right-hand side. And if you specifically take for these formulas the canonical metric on a principal circle bundle in terms of a connection on the bundle, so physicists are usually doing this, recognize this as the usual way of doing dimensional reduction. But if you just substitute these particular canonical metric and a similar decomposition for the B field, what you find is exactly the T-duality rules for the curvature, for the background flux and the curvature, which are the global things contained in the 2 form and the 1 form field. Okay, again, these formulas precisely encode my formulas that f hat is pi star of h, and well, If you do them again, you go back to this. Also the other formula, as well as the fact that h hat minus h should be, well, we saw, should be an exact form. Okay. Okay, so maybe I should give you this picture. So Boucher rules, or these T-dualities, arise from string theory by looking at actions for strings moving in a particular background with isometries, and then going through sort of an action on a sort of correspondence space where I don't have the original coordinates, but also some dual coordinates, by a process called gauging of the sigma model. And this gauge sigma model, so the sigma model on this correspondence space, is equivalent to the original one by integrating out this auxiliary field and then fixing the gauge, but it's also equivalent by doing it in a different order to some kind of dual sigma model. And the claim is that these two sigma models are just equivalent, and that's what's called T-duality, and that's how you get all the explicit transformation rules. So the next 20 slides or so, I was going to generalize this, but I'll skip that for maybe a future talk. But I think this is a good place to end. Hopefully this was somehow understandable. Thank you.
Yeah, so thank you very much for this wonderful talk. There are still quite a few people here, so are there any questions?
I think there's one chat question where okay, yeah.
Maybe I have a question, Peter.
Yeah.
Can you hear me? Oh,
I can hear you, Brian.
okay.
You.
Yes.
Let me.
So this T-duality, do you have like a more physical model where the like a partition function are same, and the T-duality like a more?
Yeah, so for a torus you can, or for circle bundles of a tora, you can explicitly calculate the partition functions. But in general, you can't solve a string theory in any arbitrary background manifold. But certainly in certain cases you can write down partition functions and indeed see that they are T-dual or more generally mirror symmetric or things like that. Yeah.
Okay, my second question is probably is that maybe there exists some kind of universal T-duality where this double vibration give you a larger universal Boltzmann, and then you can plug in whatever theory, homology theory.
Are you talking about this particular slide now?
No, I'm talking about the T-duality. Yeah, this is more a mathematical question, where maybe there's a universal T-duality, and then you have this cohomological or twisted or K-theory or twisted K-theory. Maybe you have more generalized cohomology theory, like Boltzmann theory or even elliptic cohomology level. Is there some?
Yeah, no, I think.
Is Mate still here? Maybe.
So what we have done is on twisted cohomology and twisted K theory, but definitely this can be generalized to more different objects like derived categories or.
Yes, that can be done because this Poincare line bundle, which is a K theory class, and coherent sheaves.
Yeah.
I just wonder maybe go further. Often this torus vibration, there may be some like elliptic general or elliptic homology is largely associated to torus bundle. So yeah, maybe
that sounds very plausible. I don't know enough about elliptic homology to.
So maybe some replace something if.
But some. My general philosophy would be as soon as you see circles, you can start playing these games for any kind of geometric or object or yeah.
Okay.
Basically, what you need is this correspondence, and then you're in business. So actually, I should probably say that this idea of this correspondence also shows up in what physicists call double field theory.
Okay.
Now, the way I've done it, it doesn't look like my action is sort of symmetric between the x and the dual variables. So double field theory is sort of a more symmetric approach where maybe you start over here, where the dependence on x and x hat are sort of similar, and then you go back to by essentially fixing gauges to either of the two sides.
The other direction is kind of related to the mirror symmetry, where the x hat have different geometry.
Yeah.
One is symplectic, other is complex.
As you know, mirror symmetry is closely related to T-duality.
Yes.
But yeah, it's the same idea.
This SYZ conjecture, that paper is actually, I think the paper title is called mirror symmetry is T-duality. So maybe the furthermore.
So it is a version of T-duality where the tori can degenerate over a certain point. So you need some additional structure to keep control over those singularities. So in general, you need to work in the complex setting and work in complex algebraic geometry. So this is really the differential geometric analog of that.
Okay.
Well, I mean, not that you can't deal to a certain extent with singularities. You can look at equivariant cases of this, and and Mathai and C. Wu, for instance, did similar things for orbifolds.
Okay, thank you. That's all for my questions.
So maybe one comment about Brian when he asked about elliptic genus and other things. So I did investigate this with Fei Han, and it turns out it's not an elliptic genera, but it's really Jacobi forms, which adapt well to T-duality. So that's a preprint this year at the beginning in January this year.
Okay, good. Yeah. Thank you. Thank you, Mate.
Thanks.
Any more questions?
Maybe a quick clarification about the last slide. You briefly talked about spherical T-duality.
Yeah.
You mentioned there's a bit of disconnect with the physical derivation. So does the last slide and the last couple of slides that you were doing also incorporate the calculations?
No, we don't know how to do spherical T-duality on. So as I said, it has something to do probably with M theory and supergravity. So the object there are 2 and 5 branes, so you'd have to go to maybe higher dimensional sigma models.
Okay.
But it doesn't seem to be related to an isometry, gauging of an isometry. I don't have a good answer. We just know that topologically, you can do the same thing on the level of Giesen sequence and isomorphisms between twisted cohomology and K theories. But we don't have a good understanding how it would act on even the forms themselves.
Just wanted to check if I missed something.
So there we have some idea how a particular form of generalized geometry called M geometry is relevant to this case, but we don't have a symmetry for the full dynamical, for all the degrees of freedom of M theory or something like that.
Thank you.
Yeah, maybe I have a question about that. So is there any way to have some generalization of the Busher rules in this context?
Well, yeah, so that, I mean, again, that's what we would like to have, but we don't have. We really don't know what's, I mean, so it seems like one should be able to do something by starting with a theory of 2 or 5 branes and 2 branes ending on 5 branes or something like that, and doing something like constructing some kind of correspondence space and doing this process and deriving some set of transformation rules, but we haven't found anything that seems to work.
Cool.
So it's not a 2-dimensional sigma model, right? It's
right.
But the numerology of 2 and 5 branes, 3 spheres, and I mean 7 fluxes. I mean it's almost too suggestive, and that in combination with the fact that a lot of the manifolds that physicists have been using to compactify supergravity are three-sphere bundles in some sense. So yeah, it's almost too good to be not true. But yeah, that's an open problem. I've looked at experts in supergravity at solutions that people had, see if we could find symmetries, but it all led to nothing. So.
Any more questions?
I'm happy to, of course, answer questions if people still come up with questions afterwards, and just contact me on email, and we can arrange a Zoom session or something. Or.
All right, then I'll stop recording now. And I think we all thank you again for this wonderful talk.